So here's another function that we want to try to take the antiderivative of, and assuming that you don't know how to approach this, you would hope that a regular old antiderivative formula will work. We don't have anything that really resembles what we have as the integrand here. Maybe a u substitution will work. You could try to let u equal this denominator, but if you try to go through that process, you're not going to get the right cancellation to occur with what's up in this numerator, and so that's not going to be an option either. I'm not going to go integration by parts. Integration by parts we would really typically use with products. This is a rational function, meaning it's a polynomial over a polynomial. So what I'm going to try to do is I'm going to try to take this rational function and factor its denominator. I'm going to see if I can possibly rewrite this complex rational function as the sum of three simpler rational functions and do a partial fraction decomposition with it. So if I'm trying to factor this denominator here, I can take out a common factor of x from all three terms, right? And then if I'm trying to factor a little bit further, I think I could go with 2x, and let's see, if I toss a plus 2 here, 2x times positive 2 gives me plus 4x, and if I go with a minus 1 here and an x here, outer times outer gives me positive 4x, inner times inner gives me minus 1x. I've factored this denominator. I have distinct linear factors, meaning individually this piece right here, this piece right here, and this factor right here, individually each of those is going to graph a line, and none of those is appearing more than once. Anytime you attempt to do a partial fraction decomposition and you're dealing with distinct linear factors, you're just going to break up this fraction. You're going to assume that this complex fraction can be broken up into some value over x, the first factor, plus some other value, call it b, over the second linear factor, 2x minus 1, and then plus some other constant c over the third distinct factor in this case. Now this is going to be a little tougher than a lot of the partial fraction decompositions you do, because we're trying to break this up into three fractions. If there wasn't an extra x in this denominator, we wouldn't have to worry about this, and we wouldn't have three pieces, we would just have these two. So a lot of partial fraction decompositions work out that way. I just chose to check out one that's a little tougher than that. So now what we want to do is we want to figure out how we can add these together. And to add three fractions together, we're going to need to find a common denominator. Well, the common denominator between these three separate denominators is actually staring us in the face. It's right here. If I multiply these three denominators together, I'm to this original denominator that we have just to the left. So now what I need to do is I need to figure out how I would turn each of these denominators into the common denominator. I'm going to take a minute to pause the video here, put some stuff on the page, and then come back and talk about it. So during the break there, what I did was I realized to turn this x into the common denominator, I was going to have to multiply by this factor and by this factor. So I FOILed these two denominators together, got this answer, realized I was going to have to multiply top and bottom of this fraction by 2x squared plus 3x over 2, or minus 2 over itself. I realized I was going to have to multiply this denominator by each of these two to turn it into this common one. And so I distributed x into x plus 2. Got x squared plus 2x, multiplied top and bottom of the middle fraction by 1 in the form of x squared plus 2x over x squared plus 2x. And then similarly, this denominator was going to have to get multiplied by these two denominators in order to turn it into this common one. So I distributed this x into this quantity and got 2x squared minus x. At that point, I distributed a into this trinomial, b into this binomial, c into this binomial, got this result, and I wrote it as a single fraction. I'd have the common denominator of x times 2x minus 1 times x plus 2 after doing the math I just mentioned. So I've written that as a single fraction. Once you're at this point, this fraction here should be equal to the fraction that you have back here. They have the same denominator. So basically what that means is your two numerators are going to have to equal each other. So the original numerator from back here, x squared plus 2x minus 1, is going to have to equal this whole mess of a numerator that I have right here. So 2ax squared plus 3ax minus 2a bx squared plus 2bx 2cx squared minus cx. So this numerator back here is going to have to equal the numerator down here since they have the same denominator. So now that this equation is written out, you look at it and it's a mess, right? There are x's in it, x squareds in it, a's, b's, and c's in it. A single equation with as many different unknowns, constants, and variables as this one has is usually bad. But in this case, what we can look at is we can look at the fact that the coefficient of x squared on the left side of the equation is 1. That means that 2a x squared plus b x squared plus 2c x squared will have to combine to 1x squared. That means the coefficients of the x squareds over here will have to combine to the coefficient of x squared over here, meaning 2a plus b plus 2c will have to combine to 1. So I've basically equated the coefficients of the x squareds from the right side of the equation with the coefficient of x squared from the other side. Similarly, the coefficient of x on this side is 2. That means the coefficients of the x's over here are going to have to combine to give me positive 2. So positive 2 is going to have to equal, well, the coefficient of this first x right here is 3a. So 3a plus 2b minus 1c are going to have to combine to give me a value of 2. And then lastly, we have a constant value of -1 here. That constant value of -1 is going to have to be attained by all of the constants that are over here. Now this piece has an x squared, that has an x. Well, this piece just has a constant, right? So that'll be a -2a. And if you look, all these other pieces have either x or x squared. So the only constant from the right is sitting here. That constant on the right side of the equation is going to have to equate to the constant on the left. So this is kind of nice because although a system of 3 equations and 3 unknowns is kind of tricky to solve, when you get an answer right away, like we're about to do, divide both sides by -2, and you get a value of 1/2 for a. Now what you're able to do is you're able to toss that value of a in place of the other a's, and you're going to have generated a system of equations that just contains no longer a, right? We're putting 1/2 in place of a, so it just contains b and c, and we would solve that system by either elimination or substitution. I'm going to get some work on the screen and be back to talk about it in just a sec. So I did put my answer for a in place of both a's, did a little bit of math, moved that constant value over with, in the case of this equation here, moved 2 times 1/2, 1, over to the other side with the other 1, so I subtracted 1 from 1, got a 0. Similarly, this would be a 3/2. I subtracted that from 2, and I got 1/2. So these two equations form a 2x2 system. We want to solve that 2x2 system. I'm going to solve by substitution. It's easy to take this equation and solve for b. So I'm just going to subtract 2c from the 0. So I'm claiming that b is equal to -2c. That allows me to substitute into this equation, replace b with -2c. Now I'm going to be able to solve this equation for c, so that'll be a 1/2 equals what? -4c minus 1 more, so -5c. What's c going to equal? Well, I'm just going to have to divide 1/2 by -5, and that'll give me -1/10 for c. If c is -1/10, what's b? Well, it's going to be -2 times -1/10, so that'll give us a positive value, and b will end up being equal to +2/10 or +1/5. So what does this mean? Well, I can't really show my entire screen without shrinking the window a little bit, so it's going to get a little bit smaller. But at the bottom of the screen here, we've now found the value of a, b, and c that would make this sum equal to the fraction that we started with. If we rewrite this fraction as the sum of these simpler fractions, we're going to have a situation that we can actually handle as far as anti-differentiation is concerned. So what I'm going to go ahead and do is I'm going to do a little bit of work, get a new screen going since I'm out of space on here, and we will wrap this up. Okay, so the original integral, the integrand could be factored in the denominator to look like this. We assumed that this complex fraction could be rewritten as the sum of these 3 simpler fractions, and we did a ton of algebra on the previous screen in order to determine that the constants in these numerators, a, b, and c, would be 1/2, 1/5, and -1/10. So what I did was I broke this integral up into the sum of three simpler integrals. I would have had a 1/2 in a numerator above an x. I've factored that 1/2 out in front of that integral. You can always factor a constant out in front of the integral. Similarly, if I put a 1/5 in place of this b, I could factor that out in front of the integral. And same thing with the c. If I put -1/10 in for c, I could factor that -1/10 out in front of the integral. Now I have three much simpler integrals to try and carry out here, and we will finish this up. So we're going to have 1/2 times the antiderivative of 1 over x, and the antiderivative of 1 over x is natural log of the absolute value of x. I could put a plus c here, but I'm going to have the sum of three separate antiderivatives. I'm just going to tack on the 1 plus c at the end rather than three separate plus c's. My next integral is going to be a little tougher. I'm going to have to let u equal this denominator. I'm going to need to do a u substitution here. Now if I let u equal this denominator and I go through the substitution steps, I'm going to end up with u equaling this. Du dx is then going to equal 2, and I'm going to have to put du over 2 in place of dx. So I'm going to have a constant of 1/2 sneak into this. I'm going to have 1 over u with respect to u. That's going to basically mean I'm going to have this 1/5 times the 1/2 I pick up via the substitution. So that'll be a 1/5 times a 1/2, leaving me with a 1/10. The antiderivative of 1 over u would be natural log of the absolute value of u. I'm just going to back substitute and put 2x minus 1 back in place of u. And then plus -1/10, I'm just going to do minus 1/10. Technically, I'd need to do a u substitution for the antiderivative of this, right? I'd let u equal this denominator. But if I let u equal that denominator, u equal x plus 2, my derivative du dx ends up equaling 1. I don't pick up any new constants. I'm going to have 1 over u that I'm trying to do the antiderivative of, and that's going to be natural log of the absolute value of u. Back substituting would require me to put x plus 2 back in place of u. Here's my antiderivative. It's long, it's kind of nasty. It's mainly algebra though. There's not a lot of calculus when you're going through a partial fraction decomposition. And like I said earlier, this is pretty tough because this was a 3-piece denominator, a 3-factor denominator, as opposed to a 2-factor denominator. Would have been much simpler had we not had this extra x floating around in that denominator and had to break this up into 3 separate fractions. But hopefully that has helped.